Just talk a little bit about field theory here. Like we've already talked in last year's class about gravity, but we didn't really talk about a gravitational field. Um, we just said that objects, if we place an object, and then drop it, it will accelerate down at 9.81 meters per second squared. Well, it does that because we're in a gravitational field. Any mass object has a force exerted on it near the Earth because the Earth has a gravitational field. So a field is a region where a force is exerted on an object. Gravitational fields exert force on mass. Electrical fields exert force on charge. Okay? Now, how it does that, how does an electric charge exert a force on another electric charge at a distance? Exactly how that works is far more bizarre than I want to go into here. But let's just suffice it to say that it is a something. Okay, fields actually contain energy. They can't just go away. When an electric field collapses, it actually creates a magnetic field at right angles to it, which is how electromagnetic waves propagate through space. So let's just keep hitting the right arrow here, see what comes up, right? So the symbol in gravity is we've used a lowercase g for our field strength. In electric field, we're going to use an E. We don't mean energy, we mean the electric field strength. Okay, so we've already talked about in gravity, we talk about newtons per kilogram. Okay, well, a newton per kilogram is the same as a meter per second squared, right? Because a newton is a kilogram meter per second squared, and if you divide that by kilograms, right, you get meters per second squared, right? Okay, the electric fields are in newtons per coulomb. Okay, and they tend to be really big because if we have just microcoulombs where we've got quite a few newtons of force on them. Here, like with the Van de Graaff. And then this is the formula. This is how it shows up in your data packet. We used this all last year. The force of gravity was m times g. But this is how they give it to you in the data packet. So it's a little bit different. And then they give you this formula here. But if you wanted to find the force, it would be the charge times the electric field. Here it would be the mass times the gravitational field. So it's very, very parallel form. It's kind of a neat thing that IB's done, right? The direction of gravity is down, or more specifically, toward mass, right? Electric field's a little bit more complicated because there's positive and negative electric charges, right? Whereas with masses, we're only going to deal with positive masses. Now, in theory, I've read about, maybe it's possible that there could be stuff with negative mass, but we're just going to go with positive mass here. But in electric field, we've got this is a far more difficult thing, right? It's the force on positive charge, the direction. It is what would positive charge do, right? You've heard of what would Jethro do, or what would Barack Obama do, right? But what would positive charge do? That's what we're talking about here, right? Okay. And then this is the formula that we got for the force. I'm hoping that you see that this is very parallel to the formula for the force with charge, right? And the reason is what's really going on here is that there's a forcey thing, and it's really spreading out over an area that is 4 pi r to the third, I'm sorry, r squared, okay? The particles that are mitigating, or what am I saying, mitigating? They're propagating this force are spreading out with r squared. So this r squared there is because of the geometry of three-dimensional space. Okay, and then the field, if g is F over m, if I take this force and divide by one of the masses, okay, if I take this and divide by one of the masses, right, then I get gm over r squared. Right, so one of those masses would cancel. And again, if I divide this by one of the charges, like this formula implies, I should go force divided by charge, right? If I divide these by mass, right, I should get the gravitational field here, I should get the electric field, right? So that's why you've got these formulas here. This is the formula for electric field around a point charge. This is the formula for gravitational field around a point mass. If you plug in the gravitational constant, this guy, if you plug that in here, if you plug in the mass of the Earth, 5.97 E24 kilograms, and the radius of the Earth about 6.38 E6 meters. If you plug all that in, you'll get a G of about 9.81 meters per second squared, or newtons per kilogram. Okay, so that's what these formulas are here. Let's just do some examples, and in this PowerPoint we're only going to do these guys here. And specifically, since we've already done a lot of gravity, we're going to do these guys here. Okay, we're going to use this formula, E is F over Q. Okay. So a 125 microcoulomb charge experiences a force to the right of 0.0175 newtons. What is the electric field and what's its direction? Well, E is F over Q. So it's 0.0175 newtons to the right. And then the charge is positive 125 E minus 6 coulombs. So I just have to calculate that. 0.0175 divided by 125 E minus 6. And this is 140 newtons per coulomb. And then the direction is still to the right. Now, suppose that charge had been negative. Well, we would have gotten a negative number, negative 140 newtons per coulomb to the right. Wouldn't that make it to the left? So this formula is a vector formula. This formula works. Okay, yay. Let's look at some other examples of the direction of electric field here. Okay, so for example, if the electric field is to the right, a positive charge would feel a force that way, but of course a negative charge would experience a force the other way. Okay, and the reason for that is, of course, if there's an electric field to the right, that means that there's probably positive charge over here. Negative charge would be attracted to that, and positive charge would be repelled by it, right? Or we could have negative charge here, or we could have both. We get a positive there and negative there, and positive charge would go this way, right? This is the direction of the electric field. So when we talk about the electric field, it's what would positive charge do, okay? And then negative charge, of course, does the opposite of that. Let's look at some more examples of the direction of electric field. What would positive charge do, right? Well, a positive charge here is going to go that way, right? So the field is to the right. Here, the positive charge is going to go this way, away from positive toward negative, right? Okay. Here, positive charge is going to go away, run away. Any place you put it, it's going to go. A positive charge would go directly away from this, right? So that the field lines actually go straight away from it, and it gets less and less as you get farther away. It's E is K, Q over R squared is the magnitude. Okay, so this is a battery. This is the positive side. There's a negative side. So this side's positive. This side is negative, right? So a positive charge would go down, right? So that's the direction of the electric field. And then there's the answer. Well, what's the question? Okay, so let's see. An electron travels through a region where there is a downward electric field of this. Right, so the electric field is this way. Here's an electron. What force and what acts on the electron, and what is its acceleration? Well, the force, if E is equal to F over Q, then F is EQ. All right, so the force is equal to 325 newtons per coulomb, and then an electron has a charge of negative 1.602. Now this 325 newtons per coulomb is down. Now when we calculate this, 325 times 1.602 e to the minus 19, when we calculate that, we get a force of 5.2065 times 10 to the minus 17th newtons, right? And the force is going to be negative down. Now that's confusing, but negative down is up. The force would actually be up on this thing, right? There would be your force. Okay. Well, that makes sense because an electric field, if the electric field is down, that's what positive charge would do. A self-respecting negative charge would go the other way. Okay. The math also works, right? This is 325 newtons per coulomb down, but it's times a negative charge, so we get a negative downward force. Well, the opposite of down is up, so it's up. Positive that, up, right? Okay, so that's the answer to the first question. And then what's the acceleration? Well, I can just do acceleration the way I always do it, right? F equals ma. So A is F over m. So the force is 5.2065 times 10 to the minus 17th newtons, which is not a big force, but for an electron it's a tremendous force because the mass of an electron is 9.11 times 10 to the minus 31st. This is all in the data packet, kilograms. Okay, so if I divide that by 9.11 e minus 31, that's another thing that's worth memorizing, right? Okay, I get a tremendous acceleration, 5.72 roughly times 10 to the 13th, and that's meters per second squared. Okay,